Yes, so welcome everyone. So since today is the last seminar of this semester, I want to make a very brief announcement. So basically, I would like to express on behalf of the organizing committee. I of course would thank everyone for coming. At the same time, I also would express our gratitude to the secretary from Peking University, Ms. Lu Li. She was working very hard, actually not only for this semester, but also for the last 3 years to maintain the integral pages, to build up integral pages, to make sure that the people who are who cannot attend the seminar can download the slides and etc. So I want to just say thank you. And now, Li Jun, I think as you can start the scientific part of the seminar.
Okay, thank you, Yi. It's my honor to introduce Dr. Zhangbu Xu. Zhangbu obtained his bachelor degree at USTC, University of Science and Technology of China in 1994, and then joined Yale University as a graduate student. After obtaining his PhD degree, Zhangbu stayed at Yale for a postdoc and then joined Brookhaven as a staff scientist. Zhangbu has held a lot of leadership positions, including staff spokesperson and co-spokesperson from 2014 to 2020. Zhangbu also mentored a lot of students and postdocs. Together with his postdoc students, Zhangbu recently discovered breadwinner process, vacuum bifurcations, etc. Among those scientific achievements, and today's topic is one of them. So let's welcome Zhangbu to give this seminar, tracking the baryon number at RHIC and EIC. Zhangbu, the floor is yours.
Thank you, Li Jiang, for a nice introduction, and Ian for inviting me to give the talk. Over the last few months, a few of you may have heard my talk several times, but every time I give the talk, I added something new. So I hope you actually hear something new and have comments or questions. I'm most welcome. So today I'm going to discuss about tracking the baryon numbers at RHIC, and I will briefly also touch what we are going to do at EIC. So the introduction of my seminar is on the baryon number carrier, what we did with the 3 experimental approach at RHIC, and a few different theories work on also modeling even present data results at the quark matter. I will also review some of the early theory and experimental work on PP and EP, and also EIC perspectives and requirements. So you will see I put 3 figures here. Even I'm going to use the isobar data and the beam energy scan data, although this was originally designed to do research, but it seems it's the perfect data sets for this purpose. Okay, so I will start with the very basic. If you look at the 4 fundamental interaction in nature, some of them has been discovered a few hundred years ago, and the strong interaction of QCD is only formulated in the last 50 years. So now it's the 50th years. And in that sense, it's even younger than me. So it's quite interesting and exciting to continue to discover new things. So if you look at this is one of the logo for EIC. If you look at this picture, what is the dominant feature in this picture? And if you look in every snapshot, it's actually the 3 quarks with a Y-shaped gluon connected to these 3 quarks. But most of the time, we actually put it under the rock and never discuss about it, right? So in the nuclear, although 99% of the matter mass is generated by this strong interaction and gluons, but for the most dominant feature, we kind of try to ignore it. So my talk is mainly focused on what is this and whether there is anything we can experimentally say about it and test it, right? So if you open any textbook, it will tell you proton is the lightest baryon with strictly conserved baryon numbers. And each baryon quark carry 1/3 of baryon number. Proton, of course, live forever. No one has seen it decay. Quarks are connected by gluons. And if you look at Wikipedia, you will see it looks like this even today, right? There's an alternative picture even at the beginning in the 1970s already. Scientists proposed an alternative, a Y-shaped gluon junction topology carry baryon number. So the topological number is actually strictly conserved numbers. The valence, however, the valence quarks are always connected to the end of these junctions. Most of the time, you cannot really tell. But as experimenters, we try to test this, but neither of this actually has been verified experimentally. So these are the two cases. We are trying to tell whether experimentally there are ways to actually determine which one is actually correct. So I mainly inspire or say interest on this because of this paper, which actually state there is only one way to reconstruct a gauge invariant state vector of a baryon from quarks and gluons. And it's evident from the structure of this equation that the trace of baryon number should be associated not with the valence quarks, but with a non-perturbative configuration of gluon field located at the point X or the center, which gives the junction. And Dima even proposed, say, okay, you can actually using heavy ions or PP collisions to look at it, right? And that's important because it's one thing to formulate theory, but another thing is say, okay, how do we actually test it? So less than 2 months ago, we invited Dima to give a talk at the collaboration meeting. And I just snapshot 3 slides together to make that point, which I just said before. So the baryons, if you only assign to the quarks, it actually doesn't have the gauge invariant. And what he argued, or many other people also argue, if you want to preserve gauge invariant of the baryon, you actually need a junction to be associated with it. So I mentioned many times that 20 years ago, this is actually quite popular. I mean, quite a few people actually try to implement this even in the model. And there, exactly 20 years ago, there was a workshop discussing different ways of implementing the baryon transport and how it can be done. And so specifically in also this paper, it predicts a baryon transport as a function of rapidity to be exponential with a exponential parameter 0.5. So keep this in mind. Then a few years later, Nicholas and company come up with ideas that say, if baryon junction is true, what else we can do? And there are quite many interesting stuff you can do. For example, you have a baryon junction and an anti-baryon junction. Using this, you can actually construct graphite without any quarks, right? You can construct a structure similar to carbon-60 without any quarks, just the junction and anti-junction, the ribbons, the torus, and even the tetraquarks, right? Just a anti-junction and a junction connected one leg together. Even something similar, Frank Weirjack called it bartons. So these are all quite interesting ideas and interesting possibilities what we can do. About 15 years ago, people also put this in lattice to see whether indeed the configuration will favor a Y shape. And the results is indeed true that those potential configuration seems in the balance seems to be a Y shape, but I haven't seen any progresses on this front after that, and all of the computing power increased by a lot. So you may ask, well, we haven't seen quarks, right? So how do we, let me get rid of it. We haven't seen quarks. How do you know we can actually measure the baryon number of quarks or gluons, right? So I don't know that, but we know that we can actually measure the quark electric charge, right? And there are two very famous measurements. One is using this R variable, which is basically the cross-section E plus E minus 2 HIJINGs divided by the cross-section of E plus E minus 2 mu mu. So once the lowest UD quark give you this ratio about 2, then if you have 3 S quark added in, D quark added in, then this ratio changes according to the E squares. And that's how we know the quark actually carry 1/3 and 2/3 of charges. The other way to test this is by neutrino-nucleon interactions between protons and neutrons. It will give you a ratio of 18 to 5th. And this also give you the idea that, hey, indeed, we can measure the quark electric charges, even you cannot actually see the free quarks. But as far as I know, neither there is never an experiment that, okay, I prove the quarks actually carry 1/3 of baryons, or quark actually carry 0 baryon number, and the junction carry 1. So there is no any experiment actually prove or verify one way or the other, and that's what our target, what we are trying to do. So we derive 3 approaches toward checking the origin of the baryon number. One I call star method is because of the isobar accretions, we are able to measure both charge stopping versus baryon stopping emitter rapidity and check whether there are more quark charge stopping or baryon stopping. The other one is Kharzeev's method, which we can measure the rapidity dependence of this baryon transport and look at its slope. Another method is Artru in 1991, proposed using the EP and effectively its gamma accretions. Since gamma does not carry baryon number, gold ion carry baryon number, so if you just measure one beam energy, you will see a rapidity asymmetry and can measure the slope. So RHIC give us this versatile collider and start give us a large acceptance, excellent PID to perfectly do this job, right? The beam energy scan give you the rapidity dependence. The isobar give you the charge transport and baryon transport at the same time. So this seems to be the perfect setup for such a study. So we'll start with the isobar accretions. So we use double ratios between zirconium and ruthenium. By doing that, we eliminate all the detector effect and take the double ratio, which give you a tiny number different from 1. So this is about 10 to the minus 3 when compared with 1, these double ratios. So the charge stopping difference is about 10 to the minus 3. So your error bar has to be much better than this. So at least you have to do a few tens to the minus 5th. And you need to cancel all the systematic errors to that degree to be able to do it. There has never been a measurement of total charge stopping per unit of rapidity because pi plus, pi minus interaction with material cross-section is different. K plus, K minus interaction with detector material is different. P by P is different. So it's very, very difficult measurement to do, and you have to integrate the PT to get the dq dy. So this is actually very hard. So by doing the double ratios, you actually remove the detector effect and be able to actually measure the delta Q between two isobar systems. After get this difference, then using simple algorithms, you can actually calculate the delta Q, which is this double ratio minus 1, and this is at the level 10 to the minus 3. Then you integrate over the spectra of the pion, kaon, and protons to get the delta Q. So one of the questions we have been asked is, well, we know in the CME search, we see there is a small multiplicity mismatch. Although it's only in this plot, it shows the multiplicity ratios at the same centrality. You divide it, the multiplicity mismatch is only 0.5 to 10% from central to peripheral, but it actually give you a big physical effect in CME. So how do we know this won't be the same problem for our charge difference? Because charge difference is indeed the difference between two systems. If their multiplicities are different, you will expect their delta Q to be different, even there is no charge difference, right? So in the last few weeks, we actually did this algorithm. So what you can do, I try to go through a little bit details. We basically measure 4 particles, right? Give pion as an example, pi plus, pi minus in ruthenium, pi plus, pi minus in zirconium. You can define this measurement using the delta 1 and delta 2. So you just translate 4 measurement even to 4 different independent variables. If you do delta Q and just the charge difference, you actually didn't take into account the multiplicity difference. So what you need to do is the delta Q is the charge difference in one system scaled by the multiplicity difference. And this actually gives you the formula you can expand the first 2 terms. So you can see the second term, there are 2 deltas, right? This sounds like a second order compared with first term, but first term is the difference. In fact, you will put all the number in, these 2 terms are actually at the same order, so the correction will be big if you only just calculate delta 1 minus delta 2. So that's where this double ratio actually come in. It's amazing. If you do the same thing for double ratio, it turns out it's 1 plus also exactly these two terms. No matter how mismatched the multiplicities are, the same mismatch in the delta Q also appear exactly same term in the double ratio. So that effectively, you don't even need to do anything. The double ratio automatically take the multiplicity mismatch into account. So all you need to do, the two delta Q, all you need to do is indeed measure the double ratios, and you automatically take care of the multiplicity mismatch. So that's actually amazing. Originally, we didn't try to eliminate this issue by designing the double ratio. It turned out it actually takes care of it by itself. So with all this, we are able to measure the charge stopping difference between two isobars and the balance stopping by measuring the protons P bars, Ds and D bars, and all the pi kp double ratio integrations. And then you will have the delta Q and the B. Right? You can compare with model AMPT, UrQMD. UrQMD actually can match the central collisions quite well. But if you compare the same central collisions, it actually different by about factor 3 in terms of charge. But because no one has measured charge before, so it doesn't seem to bother anyone, right? And this results has been presented by Tommy and Nico in April. So you can also take the B to delta Q scale by the initial charge difference. Right? This naively, I will expect if everything be the same, valence carried by the quarks, also charge carried by the quarks, I will naively expect it to be 1. The UrQMD, HIJING, AMPT, and PCR all predict this value to be smaller than 1, while our measurement in the center is 2. There is a centrality dependence, and we believe this is because the neutron spin between zirconium and ruthenium are different, and this indeed can be reproduced by Tranto, which take into account the neutron skin, but only using the global model to calculate how much charge overlap, how much baryon overlap. Right? So one of the questions will be, how do I know you are correct to say this is just less than 1? It's not just an arbitrary number, right? If the baryons are also carried by the quarks, as all these models actually assume it to be. So we do UrQMD. Zhangbu and his student did a lot of UrQMD trying to see whether we can see any systematics, right? So if you plot the delta Q dy divided by G over A and the baryon stopping emitter rapidity, all the system, no matter what you run, all fall in one line. And this is not, you cannot just design an arbitrary number to actually make them all at 1, right? If then you do the delta Q, dq divided by dB, this is object to what we did, B divided by Q, now it's Q divided by B. So the UrQMD is below 1 in B divided by Q, now it's bigger than 1 in Q divided by B. You can also see everything is about 1, and it approaches 1 at large systems. So I think we have a systematic. We know that this is a systematic. It's not just some arbitrary number. It can be greater than 1 or less than 1 or 0, any number you want it to be. Right? If the baryons are carried by the quarks as in UrQMD. So this is one measurement we did. The other measurement is the baryon rapidity distributions. In low energies, when we used to characterize the baryon transport by this baryon rapidity loss, and it was set at a low energy with data or these green triangles. The rapidity loss is about 1 unit of rapidity. That's why you will have an exponential of rapidity, the slope of exponential rapidity loss with a slope of 1. But when you go to higher energy, this actually breaks because higher energy seems to start to turn over. And this is easy to understand if you plot the differential, not just the average rapidity loss. You can see all the energies actually follow almost exactly the same curve. This means when you increase the energies, the tail, although the tail is the most important we want to see, but the dominant proton yields is actually at this peak at about -2, right? So it doesn't matter how you change the tail, this became dominant because this has the most protons. So we propose, instead of trying to do the average baryon rapidity loss, you basically measure at its beam energies, dn, dy, and middle rapidity, and change the beam rapidities. And the results actually is quite striking. If you look at these measurements and the slope, right? It's actually really exponential. And if you fit the slope, it's 0.61. Also very precise because every data point are almost in the same place. Right? Remember, I told you Dima and other people predict this slope should be close to 0.5. Another feature is you can measure all this in all centralities and look at its dependence. It seems like there is no dependence whatsoever. They are all lined up parallel for all the centralities. And this is actually quite amazing. So this is the second measurement. The third measurement is the gamma A. So there is only one data set in the 20 years of star, which we actually select trigger no either veto on both sides or require trigger on both sides. There is only the requirement on GDC and nothing else. So this gives us a possibility to trigger on asymmetrical photon A interactions, which you require one side has nothing, but the other side has a lot of things. So this allows us to do this gamma A analysis. And one of our postdoc, Nico, actually spent a couple of years just doing this analysis and finally get everything. And the results also look quite good. This is the final results on the proton yields, dn dy as a function of rapidity in the lab frame and antiprotons. And you can see antiproton distribution is relatively flat, while proton actually has asymmetry. And this is not because of the beam gas interaction or beam target. We're actually also doing the above gap study to eliminate the beam gas interactions, but also antiproton is flat. So this also means it cannot be just the beam gas interaction, otherwise you will get also both are symmetric. So the net proton will be the difference and you will get the slope. This slope is also about 1, much closer to the rapidity slope I mentioned before, and PCR predict a much steeper slope. So to summarize these three approaches, we have the star method. Now the conclusion is B divided by Q equal 2. And this is much bigger, more than a factor 2 higher than what the model predict. The other one is the rapidity slope. We see the slope is 0.61 and it has no centrality dependence. We also measure the gamma A accretions, the rapidity asymmetries. It's in between AA accretions and PCR. And in fact, Artru actually predict energy dependence of this slope. So everything seems to pointing to the idea that if you just assign quarks independently 1/3 of baryon number, it cannot be consistent with any of these measurements. So last quark matter in September, there are also a few presentations related to this topic. One is the baryon junction reduce the directive flow. It has been known, like at the lower energies, the V1 for the protons is much, much smaller than any models can predict. So this group, McGill, Wayan, and Brookhaven design say if I have the junction, fraction of junction, the baryon transport actually is done by the junctions, you can actually dramatically reduce this V1. And actually, if you tune it, can actually match the measurements of the proton V1. So this is actually quite interesting. So I put this as 3+1 because this is also one of the ways you can make it consistent models, right? Another one is also presented a quark matter, which they use our B to Q ratios. These are red points, are exactly our data point. And they try to tune the fractions of the baryons are stopping by the junctions, and assume charge also need to be stopped equally by other mechanisms or differently. So if you require both charge and baryons stop in the same way, you clearly underestimate the amount of baryon stopping compared with charge stopping. But it's not just all of this, right? Earlier, there are already a lot of discussions trying to explain the data with the junction. One of the famous one is HIJING-BB and HIJING-B and HIJING-BB. So this was actually done in 1998, even before the RHIC data. And the argument is, say, even compare with SPS data, if you want to have enough protons and lambda production at middle rapidity, you actually need to implement a lot more stopping than what the JSET and other baseline input need to be. And this slide actually was prepared by Nicholas last year. But he thought, well, now no one is studying baryon junction, no one cares anymore. He actually didn't give the talk, but when he realized we are doing it, he actually sent me 20 pages of the baryon junction slides, and this is number 9. Not only in SPS, but also at LHC, this was also studied. So the P/P ratio has been measured from ISR to SPS to RHIC, also to LHC. Right? These are all the measurement of P/P ratio. in PP collisions. So the red curve, which Alice used to fit, actually, we explain it's actually very consistent with our free exponential results of alpha b equals 0.61. It's almost actually exact. So the data are all consistent. So there is no inconsistent between any of the measurements. So Alice argued these results are consistent with standard model of baryon number transport and set time limit on any additional contributions. So Long actually run the HIJING and also PCR. If you run the default version at the LHC energy, you actually produce more negative charge and more antiprotons than protons. So this is kind of strange, but this is what the PCR and HIJING will give you. So if you look at the later version of PCR, it actually has final state baryon junctions, and these are some of the slides which actually Peter presented, which sure they actually call it junction baryons. So in the manual, it explains a junction topology corresponding to an Y arrangement of string has been implemented, and this also is explained in the 2003 paper. The parameters in this section should not be touched except by the experts. But there is no initial state junctions. That's what I believe. There is no interaction between junctions. So Dima call it final state baryon junctions, but there is some form of the junctions actually in the PCR default now. So I mentioned Artru proposed actually we be able to study this in EP collisions, even calculate what the slope should be, and there is a slight dependence of this slope at the lower energy compared to the higher energies, and we proposed also try to do it at EIC as well. But there also has been other measurements already. One of them is preliminary results from HERA. So the HERA kinematics of the baryon transport is almost kinematically exactly the same as at the LHC, probably 7 to 8. So their preliminary results actually is almost the same as the RHIC. So if this results is correct, you actually need a flat component. There is no a constant. There is no rapidity dependence of any slope. And this clearly is ruled out by Alice data because Alice data is more consistent with this baseline, right? So Alice data actually rule out the preliminary results from HERA and any model which claim there is a baseline, but there is no inconsistency between all the other measurements. The slope are also consistent with Alice. How about other measurement? There's an EMC measurement in 1987. So this maybe need a little more explanations. So the bottom plot is the p-bar measurement, right? So the model is JetSet62. So they use the muon energy of 280 incident on proton or deuterium target. So the anti-proton, it doesn't carry any initial flavor quarks. So it doesn't depend on whether you're changing the flavor of the target quarks, right? Proton is 2U, 1D deuterium is 2U, 2D, 3U, 3D, right? So since anti-proton doesn't associate with any of these valence quarks, it actually measures to no difference. The model also predicted there should be no any difference. But the model predicted there should be more than 20% difference when you go to protons in this measurement. But the data, although the error bar is big, seems there is no differences, right? And there is only total of 19 citations. So we try to see if we can repeat a similar measurements since it's mu P, mu D, right? So we first, the sim from Stony Brook actually try to simulate the same, exactly same kinematics using EPED and see if we can reproduce the simulations. And indeed, right, you actually can reproduce what the GSS simulation using the BGO, which is derived from PCR. So you can see the protons and deuterons, there is a more than 20% difference. When you measure the protons, the kinematics are exactly the same as EMC. And the antiprotons yields, you indeed see there is no difference. So the next step we will want to do is basically understand, say, we can reproduce the same simulations from 30 years ago. Now we can actually using the EIC kinematics and using the Q square and the PT range, we want to actually see if we can see any difference in the model, and then if the measurement can conform or rule out such a configurations where the quarks actually carry the baryon number all the way to the kinematics we measured. Right. So here, the sim also did a lot of simulations using the isobars so that we can also measure the baryons and charges at different kinematics. And from all the model simulations, these ratios are all smaller than 1. So it will be very interesting to see if EIC, this ratio from the data will be smaller than 1 or bigger than 1. And there was a second second detector EIC workshop last May, and there was people are actually quite interested in this, and this is one of the 5 golden channels proposed is going to do. So this is actually quite exciting initiative. Last Quark Meta also Tim and his students present the topology and entanglement in the baryon structure is small x, and they also predict at the EIC what the measurement will be and the slope in theta will be. If you go to high energies, there will be significant difference between whether it's baryon junction or quarks. So the ideal situations at the EIC, what we want to measure compare with what RHIC measure. RHIC measure the slope of rapidities for different centralities. We measure also gamma A rapidity distributions. But the gamma A rapidity distributions level arm is actually very short, right? And we only have 1 point B to Q, 1 data point at the top energies, and there is no energy dependencies on the B over Q. So what the ideal situation in EIC will be made doing energy scan with isobars, you will be able to measure the slope of the baryon distributions, but you also be able to measure the charge distributions. I mean, total baryon number and total charge are conserved. So at the end, they have to be displayed at a higher energy. This is lower. At lower energy, it has to be higher. So this will be 2 different slopes, and will be very interesting to measure this because the model predicts there is more charge stopping. That means the charge slope is much flatter than the baryon stopping, while the data seems to indicate the other way around. So this will be quite easy day 1 measurement if we do the energy scan with isobars. And so I guess in less than 10 years, we'll be able to know. Okay. So in conclusions and perspective, baryon number is a strictly conserved quantum number, and that's what keeps the universe as it is, right? We didn't know before what a carrier is. It has not been experimentally verified one way or the other until now. The beam energy scan, although it's designed to search for critical point, it actually provides a unique opportunity in studying baryon number transport over large unit of rapidity. RHIC isobar accretions were designed to study search for CME effect. It actually provides a unique opportunity in studying charge and baryon transport. So I feel it's very important if we experimentally verify this simple QCD topology. In QED condensed matter, we know there are all kinds of topologies, and this will be the first simple QCD topology we actually can find. So going forward to EIC, we also will be a lot of other data set we can do at RHIC, but going forward to EIC, we need small Q square, large rapidity coverage, low momentum, high jump PID to be able to do the charge transport and the baryon transport with small Q square. So this will means we want to have isobar accretion to measure charge transport. But that doesn't need to be a big system, right? Even DCM7, beryllium-7, triton, and helium-3 will do this as well. So EIC can measure the baryon junction distribution functions. And I know also give you example there already. People explore other signatures in EIC, right? So it will be very exciting this path forward and see if we can indeed conform using other measurement the simple QCD topologies. Okay, that's it. Thank you.
Thank you, Zhangbu, for this very nice talk. We have a few comments and questions in chat, so I wanted to ask those first, and then if you wanted to ask a question, please raise your hand. So we have a question for Feng. Would you like to ask your question?
Oh, yes. Very interesting talk. I'm trying to understand the talk intuitively. So you said that in STAR you have measured the difference between the baryon-stopping and the charge stopping, and you recognize this as a signal of that the signal that the baryon charge is carried by the baryon junctions. So I'm trying to understand why it is so. So in the beginning you said that for each baryon junction you have like 3 quarks at the ends, right? So intuitively the charge the quark should always move with these baryon junctions. So in that picture, I still do not understand why the charge stopping should be different from the baryon stopping, because they should move together, right?
Okay. Do I mute myself? It doesn't need to, right? I think let me find maybe one of the slide. And let me share it again. Okay, can you see my slide? In this slide, right? What the example here on the right is you can move a junction interaction with a permanent without moving the valence quarks.
Okay,
so you will break a
junction
lot of mesons in between.
Oh, okay. So the junction actually can separate from the quarks, right? the valence quark.
Separate from the valence quark doesn't mean it has to be separate from the quark, because I mean there are also other quarks in between. Right?
Okay. That's okay. Thank you.
At least that's the picture, right?
Yeah. Okay. I have actually another question. So you mentioned that the baryon junction would affect the direct flow, right? But if I understand correctly, if the heavy ion collisions can be described by the hydrodynamics, then I think the hydrodynamics do not care who carry the charges, right? The hydrodynamics only care about the energy conservation, momentum conservation, and charge conservation, but it do not care who is the carrier. So
well,
I do not understand why the baryon junction would affect the hydro behavior.
I don't know whether the debate or any of them in this meeting, but the explanation is that the junction make a more symmetric. The stopping of the junction make a more symmetric if one make this tweeter of the initial compact impact, and will make the V1 smaller. Right? It has nothing to do with hydrodynamic. It's initially how it gets stopped.
It's the initial condition. Okay, I see.
Yeah.
Okay.
Usually the V1 is due to the initial asymmetry stopping. Right?
Okay, thank you.
Okay, thank you. The next question move to Xinbai Li. Xinbai, would you like to ask your question?
Yeah, hi. Very nice presentation. I'm still trying to make this baryon junction profile clear. And at DSU you could measure at very low X down to the gluon C, and at that low X, that valence quark is not special anymore. So they are swamped in the gluon C, and there are many C quarks or anymore. So I'm wondering, will this baryon junction still looks like a Y shape, or it will have many tentacles? And first question. Another question is, has this baryon junction be considered in the previous model, like the proton mass orange or the proton spin orange, or some of the model like the gamma gold interaction, like the white mass production? Has it been considered? And if it has been implemented, what will cause the difference?
Okay, so there are quite a few questions. I guess I only can answer maybe one or two. The first question is, for any distribution, right? It won't be a step function. It suddenly disappears, suddenly jump up, right? So that's why this exponential extend all the way to LHC energies. And beyond that, I don't know, but it seems everything follow in this line, even go all the way to LHC energy, also shown by Alice. You can actually fit also this curve with the slope in P-bar to P ratio. How it behaves, say, at the 10 to the minus 10, I have no idea. By this now, it seems to be everything we measured is in this curve. There are the results I have shown in several places. SPS, which Nicholas described, the ISR DEMA also discussed how it actually can explain the multiplicity increase when you have a baryon associated with it, and all the EP mu P results, which I shown here. If I have anything else, I will already have shown it clearly. I didn't find anything else. If you know anything else, I would be like to see it. But that's all I know. I presented here. Right? So.
Okay, thank you. We have a comment.
So
yeah, please.
There is another question. This baryon junction, has it been considered in the previous model, like the mass orange or the spin orange? Yeah, so there's another question.
The only thing is, like I said, the HIJING-BES, I know it's try to implement some form of the junctions. PCR, I just show you, which has been used for many studies, also has some versions of junctions. I don't know other things, and certainly probably not. I mean, that's why although there are quite some study 20 years ago, when we brought up this in the last 3 years, many students actually have never heard of baryon junction, right? So.
Okay, gotcha. Thank you.
Okay, I see Jorgen, you have a comment on this slide and you also raise your hand, so please go ahead.
Yeah, actually the comment was answered later by slide 30, but now I have a question to slide 30 if you go there. Okay. So my comment was there is also LHC data which is relevant, but you showed them on slide 30. So my first question is this red line. Is that your red line with 0.61 or our red line which was 0.5?
Your red line was fitted with a function. If I use alpha B of 0.61 and convert into your formula, it's exactly reproduce your red line.
That's weird because we use 0.5. Okay, but that's a minor thing. But the question is, would you not expect that the stopping would be different in AA than in PP? So actually, it would be surprising if the alpha would be the same. We always have argued stopping in central heavy ions ought to be bigger.
Well, it's bigger, but it's overall everything. Every energy is bigger. The slope doesn't change, right? And that's what we see, right? All the centrality from central 0.5 to 70 to 80% to PP, it's the same slope. You have more stopping, but the factor, the scale factor is the same for all centralities.
Okay, so I have to think about, but my main point is actually, I'm not sure whether you can ever say anything about junctions from just the measurement of baryon number transport, because as you said rightly, it's a non-perturbative mechanism. You cannot calculate alpha B. In certain models, you can predict it, but there are models like the one of DIMA, which says 0.5. There are others which say it's 1, which are excluded. So whatever we measure, and we also cannot calculate what it should be for baryon transport by quarks. That's equally uncalculable. So somehow it's important to measure it, but I don't think you can use any particular value, whatever it is, and say, aha, that is because it's junction rather than quarks. And you rightly at the end say baryon junction if exists. So you seem to doubt yourself. And I think it's because we cannot make a hard prediction what it should be. Isn't it correct?
I will disagree with the sentiment. So clearly, you cannot say we no matter what we do, we don't know anything. We cannot know anything. I do feel comfortable with our measurements, with all the models which in the market we have run. If it had carried quarks, it all disagree. So I'm not. I mean, clearly, as an experimentist, which I don't know a lot of detail about the theory, that's all we can do, right? But this will also push the theory to actually say, okay, if we claim this is not true, then tell me what your predictions or how you can measure it, right?
What clearly has the current models are not in accord with the data, so that's easy. The question is, can they not be modified to adjust it? So that's indeed a question to the model builders. But given that,
I agree, but that won't be my sentiment, right? I give you an example. When we measure the baryon-stopping, UrQMD or any model, AMPT can actually easily tune to match it because rapidity loss is a parameter you can actually tune. But if you also use the quarks carry the baryon number, you can see the charge is missed by a factor of 3. So we just need to actually do measurements which can kill any arbitrary claims. Right?
I was only speaking about the baryon part, not about the baryon and weak charge part. That one is maybe more robust. That's more robust.
This is that's why we carry out this measurement, spend the isobar data to carry out this measurement, exactly try to make that point. The baryon-stopping you can tune, and for the last 30 years, that's what we did, right? We tune the PDT distribution of the arbitrary Gaussian distribution to match the data. But that, if you have additional measurement, then you can constrain, say, okay, what this need to be, right? You cannot say, hey, we should just ignore the charges because it has nothing to do with baryon-stopping. At least that's my sentiment. But you can never say, hey, this absolutely is true. As an experimentist, that's all I can say. I think Dima may have comments on this.
Let me go first. I've been waiting.
Okay.
Yeah,
Sure.
Krishna, please go ahead.
Yeah, so I'm sure Dima will disagree with Jürgen in a different way than I will. But I want to disagree with Jürgen in my way. So to me, it's instructive to go back and think about something like the MIT bag model. Nobody ever thought the MIT bag model was precisely correct, but it was very, very useful for doing hadron spectroscopy until Lattice QCD matured 30 years later and did things from first principles. And when we're talking about baryon-stopping, we have no chance of doing it from first principles at this minute. So to me, the baryon junction model is just as good as the MIT bag model was for 30 years. As a way of organizing one's thinking and trying to see what are the qualitative things that experimentalists should look for. So to Feng, the way you think about the collision of two junctions, if my fingers are the junctions, one junction here, one junction here, when two of them collide, the junctions collide and stop. The valence quarks on the ends just keep going down the beam pipe at high rapidity and don't stop. That's the core picture, which Zhangbu has been describing. Could you go back, Zhangbu? You had a slide, I think you showed it several times, where you had three methods: the star method, a second method, which had Dima's name on it, and a third method, which is gamma nucleus.
Okay. Yep.
Yeah, you had a slide like that. Yeah. There, three methods. So the Artru method. So I couldn't understand the signs there. So I want to make sure I understand it, because I think that what you've called their Artru method, the idea is now I have a gamma which is hit, the gamma comes in, it hits one of the valence quarks, it clobbers the valence quark, and the valence quark goes off, flying off in the gamma direction, but it doesn't take the baryon number with it. And so the qualitative picture should be that the baryon number does not go into the hemisphere in the direction of the gamma. The baryon number is preferentially in the direction that is opposite to the gamma direction. Is that what the data shows?
Yeah, this is the asymmetry, right? So
yeah, no, but I want to understand the signs. Which is the gamma going direction?
Gamma is going in
to the left.
Yeah.
Okay, good. So then it works there also. So
yes.
So to me, these are two simple, and the B over Q being much bigger than 1, and the one on the bottom are two simple qualitative facts about baryon stopping from data, which are natural and easy to understand with a junction model. And other people who want to try to understand them other ways should. I don't think the goal should be to try to calculate these quantitatively. Dima can disagree with me in a second, but to me, as a way of understanding these sort of gross qualitative important features of the data, the baryon junction model is it just works. But that doesn't mean it's something that can be trusted precisely. It's not like Lattice QCD or perturbative QCD. And then I had a question for, that was my comment. My question, Zhangbu, is what about proton nucleus collisions?
Yes.
And I'm thinking not just about like P lead at the LHC, P gold at RHIC, but going back to proton nucleus collisions at Fermilab from Vít Buša in the 1980s, before most of us were in the business. What we've known since going back to Vít in the 1980s is that, in a proton nucleus collision, the average stopping is around 2 units of rapidity, speaking loosely. And listening to your talk, I realized we should go back and look in the Fermilab data or look in P Gold from LHC and see whether the number of units of rapidity that the baryon stops is more units of rapidity. Does the baryon number stop by 2 and the charge stop by less? Has anyone looked at that in old proton nucleus data from Fermilab from the 80s and or proton nucleus in the collider era?
So I think they measured the PA is at the lower energies than SPS, and that they see on average those 1 unit of rapidity. That's what this e to the minus y come in. For the higher energies, as I mentioned, charge stopping is actually really hard to measure. No one, as far as I know, has ever measured the charge stopping. Like I explained, no one actually ever run the isobars, right? And it's very hard to cancel all the systematic errors because pi plus pi minus, the difference is tiny, but the detector effect already can kill you, right?
Okay, so I missed the early part of your talk. If you said it already, thank you very much. I missed the early part of your talk.
The other your question about the PA is actually really good. For a lot of measurements in the Fermilab fixed target high energy, they all measure this cloning effect at high PT. So you can effectively, you are not measuring the non-perturbative regime, right? We are actually trying to do in D gold, you can take the neutrons and untake the neutrons. So effectively, you are doing neutron peripheral goal interactions and proton peripheral goal interactions. And effectively, you can measure the delta Q and the valence stopping as well. But in D gold, these measurements are much harder. So we still try, actually a couple of students are working on this, trying to figure out, and that will be a very good measurements because in D gold, you actually can measure similar to isobar. You take the neutron to measure PA and NA and see the difference. But yeah, earlier data are taken with high luminosity, a lot of pile up. You are trying to measure a soft process, so it's very hard. So in the future, if we have this opportunity, it will be perfect.
So we should turn to Dima because he's got his hand up. But it's too bad Veet is not here. But Zhangbu, the next time either one of us sees Veet, we should ask Veet about the old Fermilab data that he is the expert on. Whether there's any way of getting at this from there. He'll be interested in the question. The answer is probably what you said. It's not possible, but we should at least ask him the question. But I think Dima should have the floor.
Right, Dima, please go ahead.
Okay, let me first try to comment on the point that Krishna made about Fermilab data and lower energy data. So the point is that junction, of course, is always there, but there are also conventional exchanges like baryon exchange, which have smaller intercept, but much larger residue. And so it's very hard to see the junction contribution at low energy. It might be there, but it's just hard to resolve it because it is completely masked by conventional exchanges. So now, just to add to what Krishna said, I would like to come to points that Jürgen raised. So first of all, of course, there is a certain amount of modeling involved in junction picture. But the very existence of the junction is not negotiable. It's just the consequence of local gauge invariance. You have to combine 3 Wilson lines at a point to make the wave function of the baryon invariant under local gauge transformations. So now the value of the intercept of junction trajectory, of course, is subject to dynamics. And in particular, at weak coupling, if you think about it, in terms of perturbative theory, you get this intercept of 1, which, as Jürgen said correctly, is rolled out by the data. But from the very early days, we realized this, that, it's kind of unreasonable to think in terms of weak coupling when you talk about junction dynamics. And if you use strong coupling and combine a limit and combine it with large N factorization, then you get this intercept of 1/2, which of course is not, exact number. There could be corrections to it. But the fact that it's a non-perturbative physics doesn't mean that you cannot compute it. For example, on the lattice, you can just compute the mass spectrum of this exotic junction, anti-junction gluons. And once you know this mass spectrum, you will know the corresponding Regge trajectory, and you will, deduce this alpha B from a first principle lattice computation. So the fact that it's non-perturbative doesn't mean that it's non-calculable. So that's it.
Has it been calculated or not?
Thank you.
Well, this 0.5, it was not just a guess, right? It was, in fact, a calculation, and
I mean, on the lattice. On the lattice, people can do it, and junctions have been identified on the lattice. So people looked at the action density. Yeah. So, for example, this one. So, this configuration is clearly seen when you look at the distribution of action density inside the baryon. But the next step would be to study the exotic junction, anti-junction gluons. So quarkless gluons that contain junction and anti-junction. So I think this is doable. But unfortunately, this was not yet done. So I think this is
but the glue balls on the lattice are hugely difficult because they couple to multi-meson channels.
Right, and it will be the case also here. And in fact, this junction story is quite old. And originally, the motivation for LEAR, one of the motivations for LEAR, low energy anti-proton ring at CERN, was to produce this narrow baryon anti-baryon resonances made of junctions and anti-junctions. And now we know that all of the states are quite broad, and they are broad precisely due to.
But Dima, from the lattice, we can learn, as some of the pictures that were on the slide a second ago, that what you have is a Y and not a triangle. I remember when I was young, people didn't know if it was a Y or a triangle, and from the lattice we can learn that it is indeed a junction. Right. But you can't calculate baryon stopping on the lattice because that's very much a Minkowski.
But here
I'm just saying. I'm speaking to Jürgen. You cannot calculate baryon stopping on the lattice because that's a dynamical question, and lattice doesn't do dynamics.
No, Krishna, but if you trust Regge theory, and we use
you need Regge theory, but that's not lattice.
Then once you know from the lattice the spectrum of this global states, you know the corresponding Regge trajectory, and then you do have to use Regge theory. But come on, we use Regge theory always. We use
We're saying the same thing, but I just wanted to say to Jürgen and others, you can't calculate baryon stopping on the lattice. You have to use not only lattice, but other theoretical input, which is what Dima's doing.
Right.
Dima and Krishna, can lattice calculate this Tesla quarks?
Can lattice calculate what?
Yes.
This Tesla quark. Instead of glue ball, this is junction, anti-junction with
Yes, and this, so this is actually easier to compute than junction, anti-junction, and this corresponding intercept can also be predicted in this large N strong coupling. So you can test it against the theoretical predictions. This is easier than glue ball made of junction and anti-junction.
But Dima,
yeah,
I
this
think
is what Veneziano argues that Tesla clock, via Tesla clock, could be the junction and anti-junction. Right?
Yeah,
but Dima, to me and Zhangbu, to me, the critique, which I'm totally fine with, I think the junction picture is very useful for all the reasons, Zhangbu, you said in the talk. But the critique is that we now know that a proton, depending on how you look at it, you can look at a proton at small x and see hundreds of C quarks and thousands of gluons. The idea that a proton is either 3 valence quarks or 3 valence quarks plus a junction can never be a precise description of the proton in QCD.
But I personally never said it. If you look, for example,
I'm not speaking. I don't think you ever did say it. I don't think you ever did say it. But for people who are not used to thinking in this way, you don't use this to try and do everything there is to know about GPDs of the proton, which is what you would need to do if you wanted to describe spin, mass, etc. The art is to use a model to describe those aspects of the physics that the model is designed to capture.
Yeah, so you have a junction connected to 3 valence quarks by strings, and each of these strings contains, a huge number of gluons, quark anti-quark pairs, and so on. So there is absolutely no contradiction whatsoever between the junction picture and, the existence of C gluons and quarks. Moreover,
there's no contradiction, but you also can't use the statement that their junctions are real and exist. You can't use that to answer every question. I'm speaking to one of the previous people who asked a question.
Well, that I totally agree, I must say. It seems like people want to say that if this is the answer, how do we explain all of this? But it cannot be explained everything just using this simple junction and 3 quarks, right? There are clearly more into it, I assume.
Thank you, Zhangbu.
Yeah, but in broader sense, the fact that baryon wave function contains this non-trivial topology encoded in the form of junction has to be imposed on all computations that we do, for the proton. It is the structure of the wave function, and it will affect, for example, the distribution of spin and all other, questions we ask about baryons as well. And, in this paper that my student David Frankler presented at Quark Method that Zhangbu mentioned, we also looked at the effect of this non-perturbative structure on spin distribution in 1+1 dimensional QCD. And there you see that this non-perturbative structure does affect the distribution of helicity inside the proton. So I think that this, baryon topology has to be taken into account, not just when we talk about baryon-stopping, but also when we talk about other aspects of baryon structure. Okay, I was talking too much, sorry. So let me just shut up.
Thank you. Thank you, Dima.
Thank you. Also, as we emphasize, this is not the end, right? Say, okay, everything is done, we just stop here. As I mentioned, we are trying to explore also many different measurements to see if we still can solidify it or find cases which actually also against it, right? So we are continuing this path. We don't just say, okay, now we prove it, let's just go away, right? So.
Okay, I think we had a great discussion here. So we almost reached the end of the seminar. So if anyone would like to ask a last minute question, please raise your hand. Okay. Also, Zhangbu, you do and Dima are organizing CFNS workshop on this topic, right, in January. So I think that will be another nice place for this discussion.
Yes, Chris and Centron, they are the chair and co-chair of the workshop. So if you would like to present or like to attend, reach out to them.
Okay, so I don't see any more raising hands, so I think we can conclude the seminar. So Yi, do you have any last word you would like to say?
I just want to say thank you all for participating in this seminar and the seminar for the whole semester. So wish you a happy new year in advance. Okay. And also happy holiday. Okay. Okay, bye.
Thank
Thank you very much.
Thank you. Yeah, thank you.
you. Bye.
Okay, bye everyone.
Thank you. Bye bye.
Bye.